Up until this point, we've mostly focused on fluids that were stationary or maybe moving really slowly or something. But now we're going to look at flowing fluids and what's called Bernoulli's equation, which allows us to calculate some different properties of fluids that are in motion. To start out with, we define how a fluid is moving in a couple of ways. So these lines of flow are kind of showing you how the fluid is moving. And if you have, smoke or something being blown through a wind tunnel, it will form these kind of nice lines, and you can see what the fluid is doing. So these are pictures in a wind tunnel. I think this is some kind of a wing or something. And so you can see the fluid flowing around it nice and smoothly. So we call this streamline or laminar flow. Laminar. There we go. If you get either the fluid going too fast or not as aerodynamic of an object, then you get these little swirling things going on here, what we call eddies or vortices, and this we call chaotic flow. And as far as math is concerned, this is not good, much trickier to calculate with, and you have to do a bunch of approximations and maybe even use chaos theory and whatnot. So we're not going to deal with these types of situations. This also creates a whole lot more drag on the object than laminar or streamline flow. So for our calculations, we are always going to assume nice uniform laminar flow and keep things good. So first equation we're going to look at is called the equation of continuity, and where this comes from is if I have a fluid flowing through this pipe, so you can just imagine water going through a pipe in your sprinkler system or your house or something. If we have laminar flow, that means everything is going smoothly. And if we look at how much water is flowing through this part of the pipe compared to this part of the pipe, they have to be equal, because if more water was coming here than was leaving here, then you would build up and you'd get a bulge in your pipe. Or if more water were leaving this part than was coming, then the pipe would eventually go dry. So you have to have the same volume per time. So we call that the volume flow rate. I'm going to go ahead and write VOL for volume because we're going to also have velocities here in a second. So the volume per time is going to be constant for both sections here. And another way to write the volume per time is the volume. Imagine the amount of water that moved from here to here. That volume had a certain area, cross-sectional area, and it moved a certain distance, delta L, and so that is the volume, that area times that distance, just like the area of a cylinder times its height. Okay, and then that was done in a certain amount of time. Well, this length over this time is just the velocity, so we have the volume per time is equal to the area times the velocity of the fluid. And because this is constant, we say that A1 V1, or this is the velocity, equals A2 V2. And this is our equation of continuity. So the area here times the velocity here equals the area here times the velocity here. And what these arrows are showing you is as the area decreases, so if this goes down, the velocity has to go up so that you still get the same product when you multiply the two. And this is why when you put your finger over the end of a hose, you are decreasing the area through which the water can travel, therefore you increase the velocity. Occasionally we will also use this equation here, the volume per time equals area times velocity. So you'll want to know that one as well. Okay, next equation is essentially the equation of conservation of energy for a fluid flowing. So we have a few different types of energy we need to deal with. One is just the kinetic energy, so that's 1/2 mv squared. We also have potential energy, so if a pipe flows uphill, it's going to slow down if a fluid flows uphill. So we have, let me erase that, sorry. We have mgy, for our gravitational potential energy. But we have another type of potential energy. I think we might have mentioned this back when we studied thermodynamics. But we also have pressure times volume. This is another type of energy stored in a compressed fluid. If you think about the units real quickly, the units of pressure are newtons per square meter times units of volume, which is meters cubed. So the square meters will cancel out with two of those three, so you'll have Newton meters, which is equal to joules. So this is energy units for a compressed fluid. So this is equal to a constant as long as we have a isolated system. And a lot of times it's easier, rather than dealing with a certain mass of fluid, it's easier to deal with the density of fluid. So if we divide all of this out by volume, divide this guy by volume, and that guy by volume, and that guy by volume, that V goes away, and we end up with just pressure. And then mass over volume here is the density of the fluid, and mass over volume there is density as well. So this is equal to a constant because we divided everything. It's not the same constant, it's that constant over V, but it's still constant. So this is Bernoulli's equation right here. And usually what we're doing, as with most conservation of energy equations, we're going to compare the energy at one location with the energy at another. So often we write this as P1 plus 1/2 rho V1 squared plus rho G. A lot of times we call this Y instead of H. So Y1 equals pressure at some other point, 1/2 rho V2. And here we assume that the density of our fluid didn't change. 1/2, where am I? Rho G Y2. And this beauty right here is known as the Bernoulli equation. And I'm going to show you how we can apply it in a few different situations. Takes a little bit of getting used to figure out when these things can cancel out and when they go to zero and things like that. So you're in luck. I'll do some examples for you. Actually, not too many examples in this video, but in the next one I will. One example, though, we can use Bernoulli's equation to find the speed of the fluid coming out of a spigot at the bottom or near the bottom of a tank. So let's start writing that big nasty thing again. 1/2 rho V1 squared plus rho GY1 and on and on. Why does this have to be so long? Crazy physicists and their love of equations. Okay, so if we say that the top of our fluid right up here is where we're going to look at the left-hand side of our equation, and right here where it's exiting the spigot is, did I say right earlier? Anyway, the left-hand side of our equation up here, right-hand side of our equation over here. So the pressure on the top here is 1 atmosphere, and when we first open that spigot, the pressure out there is also 1 atmosphere pushing in on it. So those two pressures are equal, so they will cancel out. They're both 1 atmosphere. Up here, if we have a very large tank and a relatively small spigot, then the velocity, oh, they labeled that 2 and 1. That's going to be bad. Well, let's just switch them. We'll call this 2, and we'll call this 1. Maybe I should erase those so we can see a little clearer. Alright, sorry for the confusion. So this is situation 2 and this is situation 1. Doesn't really matter whether it's left or right, right? So either way, pressures cancel out because they're the same. Now if we have a very large tank, the velocity of the water here at the top is going to be really close to zero. I mean, it will be coming down ever so slowly, but it's close enough to zero that we will call it 0. So that makes this whole term go away. It becomes 0. And then all we have to deal with is these 3 terms here. And if we move this to the other side, let me go ahead and write this out. So we've got this on one side, and this velocity here is what we're going to try to solve for. And then if we move the rho gy to the other side and factor out the rho g, then you're going to have y2 minus y1, which is just going to be the change in height. We can cancel out the density of the fluid, so it doesn't matter whether it's water or mercury or anything else. And then if we're going to solve this guy for V1, we're going to multiply that 2 over, so you're going to get 2 times g times the change in height, and that whole thing is square rooted. This is actually known as Torricelli's theorem, which is just a specific case of the Bernoulli equation, but we're going to use this quite a bit. If you just want to call this delta H or something in here, that's fine too. But you might want to make note of that. Okay. Another application of Bernoulli's equation on an airplane wing. So Bernoulli's equation is what explains flight. I really should just copy and paste this dang thing, but here we go again. Plus rho gy1 p2 1/2 rho v2 squared plus rho gy2. Thank you for your patience. Alright, so if we are going to look at the difference in the pressure on the top and the bottom of that wing, we're going to say that the height difference between the top and the bottom of the wing is insignificant. So y1 is pretty dang close to y2, which means that these two guys go away. So the only thing that's different on each side of these equations is the pressures and the velocities. So let's say that the top of the wing is situation 1 and the bottom of the wing is situation 2. Well, this is why airplane wings have this specific shape. They are kind of rounded over the top, and this was a major innovation that the Wright brothers discovered that gave them an advantage over others who tried to fly before them. So because it takes a longer path like this, it has to travel faster in order to meet up and have laminar flow. So this velocity is bigger, which means if this whole side of the equation has to be constant, then the pressure has to be smaller. And the opposite is true over here. Here we've got a lower velocity on the bottom of the wing, which means we have to have a higher pressure. And so the point is, whenever you have higher velocity fluid, you end up with lower pressure on that side. And just like we saw with buoyant forces, if you have higher pressure on the bottom and lower pressure on the top, that means a higher force on the bottom and a lower force on the top, which means you're going to get a net force upward. In this case, we would call it a lift force, and we will do calculations with this later, and often we're just interested in the difference, so you would rearrange it so you'd have P1 minus P2, just the difference in those pressures, equals 1/2 rho times V2 squared minus V1 squared. So that's, you have to know the velocities and you plug those in, and then you can find the difference in the pressure. Alright, another example of that same idea where you have higher velocity and lower pressure. And lower pressure means you're going to be sucked in that direction. So you can actually get a sailboat if you, well, obviously the wind can blow into the sail and push you in that direction, but you can get a sailboat to go into the wind. I'm not a sailor, so I don't know about this, but I've read about it and heard other people who do sail talk about it. So anyway, if you position your boat like this, so the wind is coming this way, this kind of acts like the airplane wing, where the wind will be going over this larger distance here and shorter distance there. So that's going to give you a force, as shown here, in this direction, a Bernoulli force going that way. Well, the bottom of your boat, if it's got a keel, the thing sticking down into the water, that when you get pulled this way, that keel is going to push on the water, therefore the water is going to push back due to Newton's third law. So you've got force this way and force that way. You add those two vectors together and you get a net force pulling you forward into the wind. Pretty amazing stuff. This also explains how curveballs work in baseball, or if you're not a baseball fan and you like tennis, this is how topspin works in tennis. So in baseball, if you throw the ball just right, you can get it to rotate. And so over here where the ball is kind of moving into the wind, it's going to slow down the wind a bit on this side of the ball, because just the friction between the air and the ball slows down the air over here. On this side where the ball is spinning, that's going to give a little boost to the airspeed over here. So once again, velocity goes up. That means that pressure goes down. So if you have low pressure on this side of the ball, it pulls the ball this way and causes the ball to curve. If you have a tennis ball, usually it's spinning like this, and so that causes, if you have top spin, that causes the ball to have a downward force and causes it to dive down into the court. Curved balls curve side to side because you have side to side spin on it. One last application. Animals often have two holes to their burrows, and I think one of the reasons obviously is to escape anything that comes down in there, but another reason is if they spend a lot of time down in this burrow, and if there were only one opening, they would actually get depleted of oxygen down there. And so what they try to do is to have two different heights for the holes. Not that that height changes the pressure down here, but what happens is the wind speed tends to be different at different altitudes or elevations. So if the wind is faster here than down here, that's going to cause a lower pressure here. So that's going to cause air to flow through their tunnel and replenish the oxygen, so they don't suffocate down there. And you might actually even notice this in your house. If it's really windy outside and you look in your toilets, sometimes the water level goes down, and that's because the pressure outside where the sewer line goes that's exposed to the moving air, the wind is fast, so it causes a lower pressure, and it'll suck that water down that pipe a little bit. So all kinds of cool things that are a result of Bernoulli's principle. Here I'm going to put a link to a video where kind of a crazy guy does a bunch of demos. So if you want to see some of Bernoulli in action, go ahead and click on the link. See you next time.